Okay, my voice sounds bad because I'm still sick. So this is the third part of the endocrine system, and we're going to start with the adrenal glands, and they're right here, superior to the kidney. They kind of rest on top of the kidney, and even the word adrenal, adrenal, kind of lets you know their location. The adrenal glands, if you look at this photo here, just to give you a little bit of anatomy to it, you see a capsule here in yellow, and that's just a capsule like you would think of a capsule. And then this area in here is the cortex. So going around here, this is all cortex. And in the middle here is medulla. There's a few glands that work with, like on this system. For example, like lymph nodes and the thymus. So they have a capsule cortex medulla. So the medulla is usually in the middle, and the cortex is usually more superficial to that. So here is looking at a slide of it, and right here is the capsule, and they've got it labeled here. And then within the cortex, and the cortex is not really a good slide, but within the cortex you have three different zones, three different parts. So you have what's labeled here: zona glomerulosa, zona fasciculata, zona reticularis. Alright, so there's three parts of it. The most internal being the reticularis, then the middle, which is rather long, it's about like right there, that's fasciculata, and glomerulosa is right here. And actually seeing it under a slide makes it a little bit easier. So each one of these produces something. And then also you have the medulla, which also produces something. And this slide's telling you what they produce. And we're going to talk about each one of them in more detail. So let's go to the next slide. So here it is listed again. So we're going to talk about the first one we're going to talk about, which I'll touch on the next slide, is the zona glomerulosa. They produce mineralocorticoids. One of the principal mineralocorticoids is aldosterone. Right? And aldosterone is going to act to raise sodium in the body. Again, I'm doing this with my right hand and I'm left-handed. So aldosterone encourages the reabsorption of sodium, or encourages your body to keep sodium. And when you keep sodium, that means you're going to keep water in your body. So water follows sodium. And when you keep water in your body, that's going to influence the amount of blood that you have. So the more water that you drink, for example, the more blood you have. It's the same principle behind antidiuretic hormone. And then the more blood you have, the higher the blood pressure. So aldosterone ultimately works to keep blood pressure up, or at least to prevent blood pressure from falling further. So let me get to the next slide and explain how all of this works. It starts off with, the whole thing is called renin angiotensin aldosterone pathway. So when you have like a low blood pressure, and these are reasons right here that are, these are reasons here that I'm trying to circle. Right? So if you have dehydration or sodium loss, hemorrhaging, you're bleeding, all of those things would cause a low blood volume. Right? So let me just get it back there. So all these things would cause a low blood volume. And because of that, low blood volume equals low blood pressure. All of that is going to trigger the release of renin, or as it's saying here, increased renin. right? So it's going to trigger the release of more renin by the kidneys. So renin is an enzyme. What does renin do? Renin converts angiotensinogen to angiotensin 1. So angiotensinogen is a precursor, and you know it's a precursor because it's anything that ends in OGEN. So you see the word angiotensin and then angiotensinogen. That's going to mean that it's a precursor and angiotensin is the enzyme. So renin turns this angiotensinogen into angiotensin 1. Now, whereas like right now you have angiotensinogen, if you were dehydrated, all of that would be converted into angiotensin 1. Now angiotensin 1 starts flowing around your body, and in a few places, and in particular the pulmonary capillaries, angiotensin 1 is going to get converted into angiotensin 2 by angiotensin converting enzyme. So in your pulmonary capillaries, on your pulmonary vessels, angiotensin 1 gets converted to angiotensin 2 by, and they wrote ACE here, angiotensin converting enzyme. So now we have angiotensin 2. What does the angiotensin 2 do? Well, we just follow the arrows. First thing it does is that it causes vasoconstriction of the arterioles. Arterioles are smaller than arteries, larger than capillaries. So kind of the main idea of arterioles is to increase resistance of blood flow, slow the blood flow down between the arteries and the capillaries. I envision it like you have a freeway and you have a residential street, right? And then the arterioles are going to be like a main thoroughfare, like Veterans Boulevard or Paris Road or Judge Perez, something that is in between the interstate and the residential street that you live on. So anyway, those get constricted, and when you constrict those, you raise blood pressure. So think about like a bottle of water. When you squeeze the bottle of water, what happens to the pressure inside that bottle, provided you have the cap on it? The pressure goes up. So it's that same idea. This, by the way, is the same thing as ADH. ADH is also a vasoconstrictor. So it does that, and then we follow this other arrow. Angiotensin 2 is going to go to the adrenal cortex, and it's going to cause the release of aldosterone. And they're saying here increased aldosterone. So, depending on how dehydrated you are, depending on how low the blood pressure is, you'll have more renin, more angiotensin, and more aldosterone. Aldosterone, because now we're kind of at the end here. What does aldosterone do? Causes increased sodium reabsorption. And reabsorption means you're going to keep it. You're not going to pee it out. So if you're keeping sodium, you're keeping water. And if you're keeping water, you're keeping your blood volume up. And if you're keeping blood volume up, keeping blood pressure up. So that's the whole idea of aldosterone. It's similar to antidiuretic hormone, except the antidiuretic hormone kind of directly holds water. It's the kidneys holding water, whereas aldosterone is about keeping sodium concentrations up. And by doing that, you keep water. Both antidiuretic hormone and aldosterone work as vasoconstrictors. So, two common drugs to control blood pressure are based on this chart. One is renin inhibitors. So if you can inhibit renin, if you can stop renin from being released, you've stopped this whole cycle, which means that you've stopped increased blood volume and increased blood pressure. Right? And the more common way, the older class of drugs, because renin inhibitors are only like maybe, 8, 9 years old. ACE inhibitors, angiotensin converting enzyme inhibitors. If you stop this enzyme with an ACE inhibitor, angiotensin 1 never gets converted to angiotensin 2. And again, you've stopped this whole process. It's just that you've stopped it here. Renin inhibitors stop it more at the beginning. ACE inhibitors stop angiotensin II from being made. So that's angiotensin, renin-angiotensin-aldosterone pathway. Let's talk about glucocorticoids. They are made by the zona fasciculata of the cortex. Now, glucocorticoids or steroids, they are released by ACTH, adrenocorticotropic hormone. See, the other one, renin-angiotensin-aldosterone, that had nothing to do with ACTH. That has to do with a low blood pressure and renin. It was ACTH goes to the adrenal glands, but it doesn't affect mineralocorticoids. It does affect glucocorticoids. And the main glucocorticoids are steroids, like cortisone, hydrocortisone, names similar to that. And these would be also, like in a hospital setting, these would be like the steroids that you would get. Prednisone, Medpac, like Medrol, some kind of steroid shot, right? That's a supplement of these steroids. So let's look what they do. First one is protein breakdown. And you can use protein. Remember, proteins can be used as energy, so ATP production, but more often the case, amino acids are recycled to make other proteins. So we're kind of talking here about breaking down, getting better at breaking down the protein that you eat in your food. Because we want to use that protein to make other proteins in our body, like tissue repair, something like that, right? So proteins are used to build things first, make things in your body. Then they're used for energy. And then here, on the second one, you see glucose formation. So we can convert amino acids into glucose. So you can, your body has the capacity to some extent to convert one type of energy to another type. For example, it can turn carbohydrates into some kind of proteins, and it can turn some proteins into carbohydrates and some proteins into lipids and like that. They can make each other to some extent, right? So when you make glucose out of amino acids, we call that gluco for sugar, new genesis, beginning of new sugar. So we're making glucose. Why? To make ATP. There's usually only one answer for this, and it's to make ATP. And same thing for lipolysis. If you're breaking up fat, lysis to break up lipofat. If you're breaking up fat, that's because you're going to make ATP. If you're creating more glucose, that's because you're going to make ATP. So fat and sugars are used to generate ATP. So you're increasing the amount of energy your body has. Why? Because it needs to do different things. It needs to repair something, or it needs to act on something. It's anti-inflammatory. So if you ever had like carpal tunnel or something like that, you'd see that a steroid shot or taking a pack of steroids would fix that really quick. Resistance to stress. I don't mean just physical stress, but also mental stress, what we commonly know as stress. So steroids help with that. And then finally, they're used with high doses. It it suppresses the immune response. So you would want that if you have some kind of disease that can't think of the word, autoimmune. So if your body's attacking itself, pulmonary fibrosis, or some types of rheumatoid arthritis, anything where the body's attacking itself, then you want to try to control that immune system. So you can do that with high doses of something like prednisone. So those are glucocorticoids. So again, still on the adrenal gland here. The third one is androgens made by the zona reticularis. So now we're really close to the medulla here. The zona reticularis makes androgens. And the main androgen I put right here, DHEA. You don't have to memorize dihydroepiandrosterone. We can just put DHEA. And that's the main androgen. Not too important in males. And then here, in females, it contributes to libido and manufacture of estrogens. So a lack of DHEA or low levels of DHEA sometimes correlate to levels of testosterone in women. So women have, we each have each other's hormones. It's just that in men, testosterone dominates. In women, estrogen dominates, right? But there's kind of like a balance. And if you lower estrogen, sometimes for some reason testosterone goes up. And then you can see certain traits in women, like, if estrogens are affected, you might see things like slight facial hair or something like that. So those are the three: mineralocorticoids, glucocorticoids, and androgens. Those are the three chemicals produced in the cortex. So now we go to the medulla. And the cells of the medulla, this is like the very center. So if you can, if we were to look at the adrenal gland like a Twinkie, right, this would be the cream filling of the Twinkie. The cake part is the cortex. The wrapper around the Twinkie is the capsule. The cream filling is the adrenal medulla. So those cells inside there are called chromaffin cells, and they make epinephrine and norepinephrine, adrenaline and noradrenaline, fight or flight. So with that in mind, you look at what it does. I'll do the second one first. Increases blood level of glucose and fatty acids. So again, whenever you're talking about increasing fatty acids or breaking up fatty acids or increasing the amount of glucose, that's for energy. That's to make a bunch of ATP. So your body's dumping glucose into the blood, breaking up its glycogen, making a lot of fatty acids. That's all for energy. You want a bunch of energy really quick. Then we have to deliver that ATP. Where do you want to get it to? You want to get it to your muscles, like your leg muscles, so you can run away, or your arm muscles, so you can fight instead of fleeing. So muscles, liver, and heart. You want to increase the blood flow to these places. And what organ's responsible for moving the blood around? It's the heart. So you want to increase the heart rate, make it beat a lot faster, and contractility. You want to make the ventricles of the heart force that blood out faster. So you're dumping energy into the blood, and you're getting it around the body very quick. That is essentially what epinephrine and norepinephrine do. That leaves us with the pancreas, one of the last main glands that I'm going to talk about. And the pancreas, it's essentially, it has an endocrine function and an exocrine function. So most of the pancreas is set up for the digestive system. They make all of the enzymes that break down your food. But there's an endocrine function. So the pancreas makes hormones. Right? So here's the pancreas. And a lot of people confuse the spleen with the pancreas when you're looking at like a cadaver. The pancreas is underneath the stomach. So you kind of like lift the stomach up, and then underneath there you'll see the small intestine. And that's where you're going to find the pancreas. It kind of looks like a brain material or spongy material. The look of the pancreas is quite different. Where the spleen is really on the side of the body, kind of over here. So these are called pancreatic islets. Right? And it's the pancreatic islets that make the hormones. And as you see, there's 4 different types. There's alpha cells, beta cells, delta cells, alpha, beta, delta cells, and then, okay, they're here, F cells. And then it tells you right what it does here. Secretes glucagon, beta cells secrete insulin, delta cells secrete somatostatin, F cells secrete pancreatic polypeptide. In the next slide, I have it. I should have it. I don't have it, so we'll have to talk about it. Okay, so let's start with the alpha cells. They secrete glucagon. Glucagon does the opposite of insulin. Insulin lowers blood sugar. You probably already know that. Glucagon is going to raise blood sugar. So you could look at them as antagonists. They work against each other. They do opposite things. How glucagon raises blood sugar is by breaking down glycogen. So glycogen is how glucose is stored long term. So glucose is in your blood. When you want to take glucose out of your blood, your liver and muscles pack it in as glycogen. So glucagon is going to break up glycogen and put glucose into your blood to raise your blood sugar. Insulin does the opposite. It lowers your blood sugar by taking that by taking that glucose and storing it in your liver and muscles as glycogen. Delta cells secrete somatostatin. If you remember what else that is, that's growth hormone inhibiting hormone. And another function of somatostatin is to stop the production of these two, glucagon and insulin. Finally, you have these F cells that secrete pancreatic polypeptide. Pancreatic polypeptide is going to cause the release of the digestive hormones, which we're going to talk about in another chapter. And then this slide finally kind of tells you what I was saying. So glucagon acts on liver cells to convert glycogen into glucose. So glycogen, you could look at it another way. Look at glucose as like little tiny granules of sugar, and look at glycogen as like a sugar cube. So you're storing a whole bunch of little sugar molecules together. So sugar cubes would be made in the liver and muscle. Here we're breaking it up. We're taking glycogen under the influence of glucagon. The liver and muscle is taking glycogen and breaking them up into glucose to use for energy. And insulin is going to do the opposite. It's going to convert glucose into glycogen. So that's essentially, the pancreas, or at least a quick rundown of the pancreas. There are a couple of other hormones which I discussed in class, like the inhibin, which inhibits follicle stimulating hormone, relaxin, which relaxes the cervix during dilation, and there's a few more hormones at the end of the chapter, but we'll cover those in other subsequent chapters. So as far as what I will hold you accountable for, it's most of the material presented here in these three videos.